Welcome back to the development lab again. My name is Tim Gates, by the way, also known as the PLC Professor. PLC Professor is a brand name. And over the years, because I had a tendency to do mind dumps on people and educate you whether you liked it or not, people just call me the Professor. So, many years ago when I started the PLC Professor website and YouTube channel, that's just the moniker that I use. That's the brand name. Anyway, welcome again, and we've already covered some of the initial basic stuff, interacting with the data table from your keyboard and mouse, working with a few bits, turn them on, turn them off, and then we actually got into a few rungs of logic with those internal bits or non-IO bits. In this lecture, we're going to go into more depth on buffering IO. Now, if you were looking for a real fast Chautauqua rapid learning style course, this isn't it. I try to catch everyone. I figure if you're real fast, use the fast forward. Skip through until you see something you like and then settle back in. So let's look at buffering IO. And buffering IO is extremely important with the Logix engine simply because of the non-synchronous IO update process. With the active backplane, you activated a module on the backplane and then you did an update. If it was an input module, you turned on that module's input states went onto the backplane, and then the processor read it off the backplane and put it in a memory location. Executed the ladder logic diagrams. Then when it came time to update the outputs, it would turn on an output card, put the state of those outputs on the backplane. It would go through the card and then be held for the next cycle on those outputs. Active backplane because it activated the modules one at a time. With 1756 IO and the Logix engine, each IO module has input and output information. So an input card does receive data from the processor even though it's supplying the state of inputs. And conversely, an output card sends information back to the processor that the output went on, it didn't go on, and any manner of other things that you could think of. If each IO module had its own microprocessor and RAM and firmware, why not turn all those IO cards loose doing all kinds of cool things? So the point is that an input module for 1756, it updates the memory in the processor at the requested packet interval, meaning that it just comes on its own and sends the data over the backplane anywhere in the middle of your program scan. So if you start out in your first rung of logic and you look at the state of an input, there's no guarantee that that same bit memory is going to have the same value halfway through the program because the IO cards update the memory asynchronous. It's not collect inputs, do the logic, update the outputs. One way that we get around that, and that's to buffer the IO, meaning that we bring in at the first rung or right at the beginning, we bring in the state, a snapshot of the inputs, and we put it in a word that will not change for the whole program scan. And the conclusions of the rungs go into a word or words in memory that are not going to change other than by the logic. And then at the end of the program, we send those over to the actual output words. So the program does not see any changes in inputs from the time it starts scanning until it's done. And the actual output devices don't see any change in their state from the beginning of the program scan to the end of the program scan, only at the end of the program scan. So let's pound on this a little bit more. To prevent this kind of behavior that we saw in the last video discussion, in the last section of the manual, to prevent that behavior, it is common in the industry to buffer your I/O data going to and from the backplane. So let's buffer the I/O in our lab project program. You can do this online or offline, but if you make a minor mistake online, you will have to delete the tag and start over. I suggest that in the manual that you go offline with your project. We'll do that. We'll go offline with our project. So we'll save this as sneak peek before we edit it. Go offline. Typically, I have you save the project before you change it and then save it after you change it. So you have two opportunities to save it. The reason that you want to save it before you edit it is you are less likely to accidentally overwrite the previous configuration with the new one. So if you save it and then save it again with a new name, you're not going to accidentally overwrite. Just for grins, I'm going to save this right now as L31, beginner L31 buffered I/O. You can name it anything you want. Once this gets saved, well, then it says the name is invalid. Oh, I see. I have an underscore in there. Save. I had you open up the main program tag database. Go to Edit Tags tab so you can add a new tag and create two new tags. I had to create these two new tags as Dedents, double integers, 32-bit words. And you might be thinking, well, there's only 6 inputs and 4 outputs, so why not have single integers, 8 bits? But remember that the memory array in the chipset, in the processor, is 32-bit. You're not really saving any memory by using a single integer instead of a double integer. Plus, if you decided you wanted to produce or consume any of these tags, that's a very advanced subject. But basically it means that you can set up a tag as being produced from a processor out onto the backplane through a bridge card out onto some network anywhere in the whole world, and then somewhere out there you're setting up a processor to consume it. So anytime you produce that tag, that processor or processors out there can consume it. Regardless of whether it's a Boolean, single integer, or integer, when you go to produce it, it's going to be changed to a dent. So it actually runs a little slower producing a Boolean than it does producing a dent over the backplane out onto the network. We'll just make them dents. Keep in mind that each of these is a 32-bit double integer. All bits are there in memory and they are all accessible read and write. However, we have reserved that space in memory for access to just 6 bits from one of the dents and 4 bits from the other. So I had you expand these, and unfortunately you can't see both simultaneously because they are dents. If we'd have made them single integers, then we could have been able to see them both on the screen at the same time, which is not really that important. Okay, then I had you add 2 new rungs. I had you add one at the beginning before I leave here. Input slot 1, we're going to use 0 through 5. Then down here for outputs, we're going to use 0 through 3. However, we will be exercising both dents. So I had you add 2 rungs. So I'm going to drag a rung down here and drag another one down here. And in the top rung, I had you, there's several ways you can do this to get over to the right instruction. I could just type in MOV and that would have worked. I'll do that. On that rung, MOV, enter. See, there's a move instruction. It's really a word copy. You're not moving it. If you move something, then it's where it is now and not where it was before. So it's not really a move, but word copy, that acronym was already used, so they use move. So an MOV, move instruction, is not really a move, it's a word copy. Nonetheless, that's one way to get the instruction in there. So let me delete this. The other way is to scroll over through your tabbed instruction set, move logical. You could double click here or you could drag it down and drop it in there. And we're going to do the same thing. We'll go down here, click on the begin of the rung and just click. Bang, it's in there. So there's our 2 move instructions. And I asked you how many memes there were. Well, if we pick this up and drag it around, look at all the memes. They're all saying, drop it here, me. Well, we want it there. Here's the real danger in dragging things around. If you have a very complex code and you grab, let's say, an address and you want it to go here, but you accidentally bring it low, that one's green, but then you bobble a little bit and let go at the wrong time, it's going to go to not the one that you want. If you're dragging things around, you got to be real careful what you're doing. Then I had you open the source on one of them. Well, we'll do it the way we did it in the manual. Drop down and we want to move local 1i data. We want that whole word. It's actually single integer. And we're going to move it into the tag that we created. See, notice the type forward. When I had just IN, it came up with the tag IN00. Add a P, and it jumps right to the one that you wanted, input slots 1. At the beginning of the program scan, it's going to take and move that IO input data word into this tag that we created. Then consequently down here, our source, because remember now that we're buffering our IO, this is going to be out. See, it came up out 0. Add a P for type forward, and we've got it. And now this we want to go to the output data word. We've introduced a new instruction here, the move instruction. That's what we call it, the MOV, move instruction. Just keep in mind you're not moving anything. I know I mentioned that before. People forget. It's not a move, it's a word copy. But we call it move. Here we go. The very first program scan, we take and we copy whatever is in that input memory, that input data memory location. We move it into this tag. Now we're going to use these tags right here, input slot 1 for our inputs, and these tags, output slot 1 for our outputs. Rather than going through everything that we did in the manual, I'm just going to take and cheat here. I'm going to grab input slot 1. I'm not moving this, I'm taking a copy of it over to here. And of course that's a double integer. We don't want a double integer, but we're talking about bit 0. Copy that down here. So now we have input slot 1 bit 0, which is the same as local 1i data dot 0. And then here we want our outputs. And we'll make that so I think you see what we're doing here. Really straightforward. Now you have both the inputs and the outputs buffered and isolated from any non-synchronous update of either inputs or outputs. And if you read down through those rungs, you could say that at the beginning of the program scan, in rung 0, the inputs are refreshed, or rather this tag, its bits are refreshed by that instantaneous state of that word. Then, using that refreshed internal tag, we run our logic, and then once we're done with the logic, we take the results of the logic, we move it into an actual module defined tag, and out it goes to the output cards. Okay, I just saved this program as in out buffered. At this point, I'll save it again, and it was in out. I may have even had you abbreviated. I've got it buffered, B-U-F-R-D. I'll just leave it this way. Remember, the name is arbitrary. It's to help you find your different stages of your code if you want to back up and do something over. We'll save this, and now we're going to download whoactive, processors picked, download. Thinking, slower than molasses in January. Okay, here we are back in the run mode, and notice that everything is nice and quiet. Last man wins. This rung says it's on, this rung says it's off. Last man wins. So right after this bit is turned on, then turned off. This bit is actually turned on. At the end of this rung, when this rung is scanned, it turns that bit on. And then within 10 microseconds, it reads this rung and turns it right back off. That rung, oh, there, I just saw it flicker. If you have your thinking cap on and you're really pondering this situation, then you can see that this is much more stable. By the way, we do have the warning. We'll go down here and scroll up. It's the same thing. Duplicate destructive bit reference detected. Main program outputs, blah, blah, blah. These two OTEs. It does occur to me why we do see this flicker on once in a while. It is not flickering at the actual output. So the actual output itself is not flickering on. Let's say we wanted to capture that to see if this actually was turning, even though we see this turning on, is that bit turning on? Bit 0 of the output data. How would you trap that? Well, we're going to jump ahead here. This is free. This wasn't in the manual. It's something that I find interesting. So I'm going to take this tag, drag it down here, edit the tag to be just bit 0. You can't read a word with that type of instruction. We'll call this gotcha. Okay, that's a new tag name, new gotcha. Boolean, main program, finalize all edits. Now we'll drag that down and wait till we see this turn highlight to show that that bit, see that bit went on, it just went on. But if I look at the buffer data, that's not going on. Just because you see it go on here doesn't mean that that bit of this word got transferred to this word. So remember, I told you that the screen hooked to the video display hardware in my laptop through the chipset, through the USB port, through the USB to 232 converter, to the 232 port on that L31. There's no way in the world that that string of electronics could ever keep up with the rate of change in that processor. It's just not possible. What you're seeing here, this is really interesting. This is a freebie. You see this bit going on in memory because it is going on. Remember, I told you this rung is true, turns that bit on. This rung is false, turns that bit off. So guess what? This graphical user interface, RSLogix 5000, is looking at the data table. It's not looking at the code. This ladder logic you see here, that's a figment of our imagination. It only exists to present a relationship of the data with the machine level language that's in there executing the code right now. We are actually looking directly at that bit in memory. We're not looking at the result of the logic. So this is something definitely to keep in mind. And this proves that point emphatically, that when you see this change state, it's changing state in memory. But it's not going from the memory out to this word and then out to the output device. Otherwise, remember that this is local 1.0 data. This is local 1.0 data bit 0. If this were to be true, it would latch that bit on and it would stay on. I don't have an unlatch anywhere. Very interesting.